So now let's try and see how I can sort of finish this proof for you. Quite easy. So here's the first observation. Let me see if I have the graph still. There I have the graph. Very nice. So here's the first observation. So towards this answer. That due to the symmetry of the function, so let me color this part in green. The green area till this line, right? This green area is the same as the purple area on this side. So that should be clear just by the picture for sure. But otherwise also, what's the green area, the pink area? The pink area is minus infinity, 0 to infinity of e to the minus z squared by 2 over root 2 pi dz. That's the pink area, right? And what's the green area? The green area is 0 to minus infinity to 0 e to the minus z squared by 2 over square root 2 pi dz. So these two are equal. Either you can show it in analysis 2 or look at the picture and decide the area is the same, or you can just do a substitution that u is equal to minus z. But you learn this perhaps in analysis 2. So that's the first thing. The green and the pink are the same. So once you're there, and you also know the green plus the pink is what? So the green, let me duplicate that. The green plus the pink. Oh, sorry, I duplicated. The green plus the pink is going to be what now? Come on. Okay, that's very good. The green plus the pink we know is the same as minus infinity to infinity e to the minus z squared by 2 by root 2 pi dz, and that's going to be equal to 1. So the green plus the pink is 1, and the green and the pink are equal. That means that each of the green and the pink is just a half. Right? That is from this line. Right? From, let me call this as stop. So green and the pink are equal, and they're both half because they sum up to 1. So that's very good. So now we can go back and answer this question. So now, so therefore, for any a positive, right? Let's say any a positive, integral minus infinity to a e to the minus z squared by 2 over root 2 pi dz, right? What's that going to be? That's going to be, let's copy the function again, come here again, let me erase all these guys. Very good, let me erase all these guys. So a is here, right? So the integral is the entire region below this, but I'll write it like this black part, right? And this maroon part, which we know is half, or maybe the green part, like a blue. So that's going to be equal to minus infinity to 0 e to the minus z squared by 2 over root 2 pi dz plus integral from 0 to a e to the minus z squared by 2 over root 2 pi dz. And this person I know is half, right? So Therefore, which is equal to 1/2 plus this percent. So again, if I know the values of 0 to a e to the minus z squared by 2 squared 2 pi dz, then I can find out minus infinity to a e to the minus z squared by 2 squared 2 pi. So therefore, so we have down on this side I have 0 to infinity e to the minus z squared, minus infinity to a e to the minus z squared by 2 over square root 2 pi dz is equal to this. So for a positive, so for this calculation, if a is positive, the observation here is that it's enough to tabulate these values. Right? It is enough to tabulate such integrals. Right? That is, let's call this as plus. Okay. So 0. If I know 0 to a for a positive of these integrals, then I can compute minus infinity to a of this. Very good. That's one of them. So let's make this as green again. And let me make this as in some color. Let's say pink. Let's say okay, this color. So this color we can do this. So if a is positive, then these integrals are given by these colors. Okay. So what happens when a is negative? Let me go to the next page. What happens when a is negative? So let me do a different color. Let me do, let's say, a is negative. Let me do a different color. You see, this one. Very good. Very good. This color. Okay. A is negative. So I have minus infinity to a e to the minus z squared by 2 dz over square root of 2 pi. So I want to compute this integral, right? So what's that equal to? So now let's do the graph again. The graph comes here. Let me erase this part. Very good. So a is negative. So a is somewhere here. This is where a is, right? And I want this area, right? So I want this area. So now the observation is that this area, which let me call it as okay, this area right here, which I want to compute, right? Right. So now that's got to be computed from just positive understanding. So first observation is that you go back to the previous one that we did a long time back, that at minus alpha is the same as this alpha on this side, right? As this alpha. So let me get this down. This area is the same as, so the area, let me take an area under the curve in this region. Very good. It is the same, if you go by observation, it's the same. Let me put this picture down again. Let me bring it down. It's the same as, let me erase all this. Very good. The same as, I can go to this side, now minus a is positive, and I have the same area here. Same as area under this region. Under the curve, in this region. Very cool. Right. So now I have transferred something this, but this we also know from the other observation that this is. So let me copy this down again. This down again. So I'm deliberately not doing by integration because I don't want you to use I want to understand the geometry of it all. So same as I put this point minus a here, same as, let me copy this whole thing in red, is this thing is the same as 1 minus, so 1 minus the area under this region, right? Area under. Quite cool. But this is now positive now. But this is again the same as, let me bring this down. I'll bring one picture down here. This is this. And here is again. This, and then let me bring one more picture down. This above is going to be the same as the area under the green region all the way to 0 plus what we can calculate, that is these people. My internet again is, this is the point, minus a. Very nice. So let me just recap this calculation. So what did I do? I start off with, it's a little bit picture, prove a picture. So for A negative, I had a little jugglery. That's the area I want to calculate. The first step I do is I say that, okay, fine. On this side, I say that I split up as the area on the other side, which is 1 minus the area on, so I should write 1 minus. 1 minus this area. Okay. But this particular person here is going to be equal to 1 minus this picture right here. So here is this equal to 1 minus this picture. So therefore, I began with this integral, right, is equal to this area. This area is by symmetry. This 1 minus this by probability ideas. And now I'm on my way. So what is this going to be equal to? This is going to be equal to, this part is half. So it's 1 minus, this part is half. So it's half. And this part is just 0 to minus a e to the minus z squared by 2 over square root 2 pi dz. Very cool. Right? So that's how I did this for A negative. So let me just summarize this part now. So what do I finally get here? I get that, so what do I finally get? I get my 0 to A for A negative, sorry, A negative, not 0 to A negative minus infinity to A e to the minus z squared by 2 over square root 2 pi dz is equal to, on this side I have 1 minus a half, that's minus, it's just a half, plus minus this guy is 0 to minus a e to the minus z squared by 2 over square root 2 pi dz. So again, for a negative, it's also enough to understand these integrals. So same as I had here. Okay, let me just so enough to understand these integrals. So for both negative and positive, if I want to understand minus infinity a e to the minus z squared by 2, if it's negative, then I had to have a half minus the integral from 0 to minus a. If it's positive, I just have half plus that integral. So then from these two calculations, let me call this as calculation 1. Let me call this as calculation 2. So from 1 and 2, claim is shown. 1 and 2, probability of a less than z less than equal to b, which is equal to minus infinity to a minus infinity to b e to the minus z squared by 2 over square root 2 pi dz, minus infinity to b e to the minus z squared by 2 dz minus infinity to a e to the minus z squared by 2 square root 2 pi dz can be computed from tabulated values of integral from 0 to a, 0 to alpha, e to the minus z squared by 2 dz over square root 2 pi alpha positive. That's the clue. So if I know only these people, then I'm in good shape. So that's how you work with normal random variables. You don't since you can't compute the integrals directly, you have to use these sort of tables to do this. Okay, very good. So let me quickly recap, and I will close with one new distribution, which is from this class of normal random variables. I'll stop with that. So let me start off from the beginning. So normal random variable is a random variable with this density function. So the first thing we observed was the normal random variable has a lot of interesting symmetries, and these symmetries can be used to your advantage, even though the integral has no antiderivative and you can't compute the probabilities directly. So you have to be a little careful when you do this computation. So now the first observation is that the integral a to b of this function is just the area under the curve. Then the next observation is that, so let me make it why is it answer 3? I have no idea. Okay, how does one compute probability? So let me call these as observations 1. So let me change it, observation 1. Let me make it in pink. So let's see. So observation 1 is that the integral on this side from to minus alpha is the same as alpha to infinity of z on that side. So here alpha is positive. So here alpha is positive. And that's the same as this example right here. Now, this is sort of a key thing to write down, that this is true. That's the observation you have taken. Right. Then I said that, okay, fine. I want to compute the chance that A is between Z and B. Right? That's what I was after. So then I came to the idea that this is the same as integral A to B of this integral, which is minus infinity to B and minus infinity to A. So then all I had to do is I said that it's enough to compute only these values of integral, 0 to alpha for alpha positive, to compute this one. And the way we achieve that is what sort of jugglery. So the first observation is observation 2. Let's say observation 2. Very important. Keep in mind that that these integrals are divided on each side. So each area around 0 is half. That's the first observation. Then I said, once I have that, then I'm on my way. Because for A positive, the answer is quite easy. It's just, I just think of it as half plus 0 to A. So it's enough to have these integrals in mind and tabulate. For A negative, you have to be a little bit careful. What you first do is use symmetry to get minus A to infinity. Then once you have this, then again you have, this is the same as 1 minus this whole thing, because the whole area is 1. And once you have that, you're on your way, because that's just the same as 1 minus a half plus this area, which is 1 minus, which is half minus this area. This is the final answer. So for positive, you have just the integral half plus that. For negative, you have half minus the other part. Very nice. So I'll close with one last observation, and then So in general, the normal random variable comes with two other parameters. So we say, here's definition. We say X is normal. Say X is normal with parameters mu and sigma squared, where mu is positive, mu is a real number, any real number, and sigma is positive. If X has a PDF given by f sub x at x was e to the minus x minus mu the whole squared by 2 sigma squared, whole thing divided by root 2 pi times sigma. This is for x and r. So this is a general definition of normal. Previously we had discovered, Z was normal 0, 1. So that is mu was equal to 0 and sigma was equal to 1. So it's consistent. I just didn't do the general definition first because I didn't want to do the symmetry across. So I just decided to do it like this. So today's class we have understood how normal came about. It came about as limits of binomial. The next thing we understood is that how to compute the probabilities of normal. And that's given only by the tabulated values of normal random variables. Now let me try and see if I can show you. Let's try and see if I can get this for you to see, check if it's available for you. Then I think I'll close with that discussion. Is that these tables are available on the internet many places, but I think in my book I have kept it in the appendix. So let me just check if I have it on the online version. So I'll stop with that. Okay, it's not given for you. So I will supply to you over chat or on the class website I will leave the normal tables. So let me write that down. So on the class website, I will place normal tables of integral 0 to a e to the minus x squared by 2 dx by root 2 pi. So I'll place it so you can sort of work with them.